Well, we don't have the time to go back to all those through the problem-solving loop, but you remember how we get it. Look at the assumption, and the key difference is the friction, or say damping effect, make it the whole difference. And the equation all based on the first principle, Newton's law and the Hooke's law. The second system is this. I have a coupled spring mass system. The coupled spring mass system is like this. I got a smooth side surface, and then put one spring here. I call it the stiffness is K1. I got the one mass here, is M1, and I got another spring in the middle, and the second mass here is hooked all. The third one here, and now hooked to that end. And then I have 3 springs and the 2 masses. That's called a coupled spring mass system. Now, to get this system, it's a little bit tricky. You need to look at the Newton's law in 2 different coordinates. The first one, let's say you don't apply any force to the system, and this M1 stay here as the equilibrium point with x equals 0, and the M2 stay here, the y equals 0. These are the coordinates of the 2 systems. Let's put it this way as the positive direction for the x, and this way the positive direction for y. And now you think about the Newton's law. The M1 times the acceleration of the first mass should equal the resistance from the 2 springs applied on this point. So the first one's easy. It is negative because it's resistance K1 X. That's the change. The second one's a little tricky. This X move rightward, and then the spring K2 will push it backward. But push how much? It's not exactly X, because the Y could go to the same way, could yield like a little bit of this. And then your real moving distance is going to be the X minus Y. Depends on how much Y moved away. That's the first equation. The second equation, this side is relatively easy. But let me put the easy one first. K3Y, because that side does not move. And this side, if you move this way, it will be pushed in the positive direction. Then you minus K2, and the distance should be exactly the opposite. Y minus X. Depends on how much the X yield. So I will let you think if you have a little trouble to follow. It's just because these two are both moving. Now, once we get this equation, all we need is divide by M1 in the first equation, and you divide, we rewrite a little bit. See, this x combined with this x is negative k1 minus k2. That's k1, negative k2. And this m1 divided from the other side. And the second term, k2, y, negative, negative, make it positive. That's how you get this. The second one, see the k2 is right here, y, that's positive. No, that's negative. The x, k2x, negative, negative, make a positive. That's right. And divide the m2 from here. And then, look, negative k3, negative k2 is right here, divided by m2. And that's straight algebra. So what do we get? In this system, it's a little bit more complicated. So what is that? Look at the two derivatives. You call it the second order. Second order. And you have two variables. Then it's a system equation. Is that linear? Of course, linear. There's nothing with a second degree. So, turned out this system is a second order linear system. But we cannot solve second order. We can do the same thing as we did before. Introduce a velocity v for the x, the first mass, a velocity w for the second mass. And then the other side, this xy and the xy are the same. So we got a trade-off. Instead of second order, see, you all got the first order. Why? Because v equal x prime, x double prime is simply v prime. See? That's x double prime. And the w equal y prime, then the y double prime is simply the w prime. That's the second equation. So if I write it into matrix form, see this is derivative. This will be a 4 by 4 matrix. Not too bad. 4 by 4 in real application, that's almost nothing. Once you build this system, I can build the standard model. Look, because you have 4 variables, how many tanks we have? 4. And what are the 4? This is the x, this is the y, this is the v, and this is w. A little bonus. If you write the program, you better not use those mathematics notation, because your program is for the human to understand it. In order to let a human read your program, you would like call a name, always remind what is it. So I give the position, velocity, instead of just calling x, y, vw. That will help your model more understandable. Okay, so how to build the model? It's very simple. The change of position is velocity, and then here, all you need is put v here. And the change of the position is velocity. In here, all you need is put w here as a mathematics model. And that's why you need this information link. Can you see it? The second one is a little harder. The change of the velocity is the acceleration. So in this case, you need to put all those mass expression on this side For the first one, this side. For the second one, you remember it related with the x, y, and all the parameters. So what you see, the x, look, the exception x goes to here, and the y goes to here, and also the y also go to here, and the y also go to here. That's the two variables you related with the x and the y, x and the y. How about other things? Those converters, that's the mass, resistance, what else? Resistance, and those are the parameters you have. So you build the model. And when you run the model, what you get? It's not a surprise. Because in the model, we don't have any resistance or damping. You got the two harmonic motion superimposed each other. And then if you add the two sine wave or two cosine wave with different frequencies, this is what you get. You're going to get this blue curve, which is the velocity of y, and that's actually velocity of x, and the position of x, velocity of y, position of y, and you can see they're really bouncing with different phases, but the same frequency. How can you explain that? The explain is here, eigenvalue. If you try to solve this eigenvalue problem, you remember your A is not that bad. If I let it make it simple, k equal 1, and make this m1 equal m2 equal 1, that's how I make things easy. And then your system equation is 0, 1, 0, 0, and let me see. And then this will be negative 2, 1, 1, negative 2. Okay. Okay, that's negative 2, 0, 1, 0. You're going to get a system like this. If you find the eigenvalue, you bet this, you have two eigenvalues. Is square root of 5, positive and negative I, and then 1 I. That will give you these two frequencies. And you can use Maple to solve it. I give you the command the last time. And that explains the phenomenon.